All right, now it's time to talk about specific properties of a gas. Okay, then we're going to work our way through liquid, then we're going to work our way through solid. So the ideal gas law comes from various pieces from various French physicists. For example, pressure versus temperature is the idea if I have a gas where these particles are free to move around whichever way they move, and I increase the temperature, then they're going to hit things harder, and pressure, which we're going to discuss in more detail later, is essentially force, or force per unit area. So because of that, this situation, this second situation over here, has to have more pressure. And so I say, as the temperature goes up, the pressure must also go up, right? And so that leads to a strange pressure before divided by temperature before equals pressure after, temperature after. And I have to divide because it's the only way to make it so that when one goes up, the other has to go up as well. Okay? And such, this ends up being part of the ideal gas law. Okay? I'll try to put together a demo for you later on these. The bottom line is the more the temperature, the more pressure. Now, we do need to remember that at 0 degrees, this thing turns really odd. What it says is you have an undefined pressure at 0 degrees. That makes no sense at all. And Celsius makes perfect sense in absolute zero land, because at absolute zero land, the particles are not moving, so not applying any pressure, but they also can't move because that means they would have temperature, and so therefore they'd have infinite pressure in the sense that you couldn't collapse it downwards. That's an undefined pressure. So we must use a Kelvin scale when dealing with the ideal gas law. All right? So pressure versus temperature is that idea. Then we move forward. We talk about the second one, which is temperature versus volume, which has much the same thing. If I keep the pressure the same, then if I have these particles moving like this in some sort of a container and I heat them up, I increase the temperature, then what happens is the particles are going faster, they hit the sides of the container harder, which means they win the battle, and so the container must by definition become bigger. Agreed? Okay, so as such, we use the exact same formula. Say V over T equals V over T, and again, the same idea. If you have 0 absolute value, if you have 0 degrees Celsius, that means your volume can't be defined. It makes no sense at all. So you can't use Celsius, you must use degrees Kelvin using this version of the law. And then the last piece of the puzzle is if I have pressure versus volume. If I have particles and they're moving and they're happy, but I'm not changing the speed of the particles because they're not changing the temperature, then what happens when I increase the pressure? In other words, I start to squeeze from every side inwards. Well, the particles aren't changing their velocity, then they're colliding with the side of the container with the exact same speed, therefore they start losing the battle, and the container would collapse downwards. So as one goes up, the other must go down. So we'd use this particular idea, or what's called the inverse variation. So far, so good. So because of that, we put it all together and put the physics formula for the ideal gas law. The physics formula for the ideal gas law is PV over T equals PV over T. All right, moving forward. PV over T has some weird unit issues. First of all, this must be in degrees Kelvin. Have to. Volume, we're not very picky about. We'll typically use liters, but we could use meters cubed just as easily, and actually meters cubed is a better unit for us. But you could use liters or meters cubed and it wouldn't be a problem. Pressure, unfortunately, was discovered a long time ago, so it has all sorts of stupid units that we don't like to use. The best unit for us is something called a Pascal, which is little p little a. Pascal is a Newton per meter squared, which makes sense because we said before it's force per unit area. Okay, in other words, if I double the area applied by a gas, where force is applied, I get twice the force, and so forth. We'll talk more about pressure in just a little bit. So pascals in Newton per meter squared, which is a convenient unit. Unfortunately, at sea level, it is 101,300 pascals is normal air pressure. That's a very big number for very little effect. So the other unit we might use from time to time is atmosphere. Specifically, 1 atmosphere is the pressure you would have at sea level, which is 101.3 kilopascals, or 101,300 pascals. Fair enough? All right, let's see what we can do with this. Okay, go to A2 now. A2. Here we go. Go ahead and try the first problem if you can. It shouldn't take you very long. Start this up when you're ready. Okay, a volume of 5 meters cubed of gas is expanded to become 12.5 meters cubed. The original pressure was 2.00 times 10 to the 6 kilopascals. That's a big K, should be big K, little p. That's a little weird. Okay, but then the final, what is the final pressure? So we're going to pressure at the end. Okay, so I go PV over T equals PV over T. Temperature doesn't change, so I simply cancel it out. It becomes one of my mini laws. One of those 3 laws we just talked about a second ago. So I end up with pressure, which is 2.00 times 10 to the 6th times 5 equals pressure, which I don't know, volume, which is 12.5. So now I'm going to get out my calculator, move it across. So I get 5 times 2 exponent 6 divided by 12.5, and I get my pressure is, and again, I'm going to use the same unit I have over here, but I'm going to get 8.00 times 10 to the 1, 2, 3, 4, 5, 6 kilopascals, which is an awful lot of pressure, by the way. So far, so good? All right, so that's how that one works. Okay, try that next one, number 2. All right, starting number 2 now, so hopefully you get a chance to do it. Number 2, here we go. Pressure acting on a 60.3 meter cubed gas is raised from 236 kilopascals to afterwards I have 354 kilopascals. Temperature is kept constant every time. What's the new volume? So I'm going to go PV over T equals PV over T again. I get pressure, which is 236. If I wrote that better, 60.3 equals 354 times volume. Again, temperatures cancel out because they don't change, so therefore they have no effect on the problem. And I do the math, and we're done with that. Okay, so you should be ready to start 8.6 and do it to completion.